Welcome! In this presentation I would like to tell you about how we characterize 3D printed sheets using multi-frequency scanning impedance tomography. I will start with an introduction of why we do this. Then I will explain what we, based on our model, expect to measure using this technique. After that I will explain the measurement setup and show the results, and then finally I will explain and discuss the conclusions that we drew from this. So first, why do we want to characterize 3D printed sheets? Well, as we all know, 3D printing can be used to fabricate complex systems with less assembly, and with multi-material 3D printing it also becomes possible to fabricate complex systems with integrated sensors. However, 3D printing sensors does pretty much always require conductors to be printed, and as we have seen over the last years, these conductors don't always behave like the solid conductors that we are used to. Instead, they are anisotropic and non-uniform. We expect that this is due to the fabrication process, which for FDM consists of lines of filament, which we call traxels, which sometimes are good and sometimes are not so good connected to each other. In this case, they behave similar to coupled lossy transmission lines, as shown in this circuit. And to be able to better understand this, we have previously characterized sheets of 3D printed material using lock-in tomography, and here a current is sent through the sheet and a thermal camera is used to measure the heat that is generated, with the idea that due to the anisotropy, some parts will get hotter as others. Also, we have characterized the anisotropy using voltage scanning electron microscopy. Here we use that the contrast that you get in a SEM is dependent on the voltage on the sample. However, both these methods were only suitable for qualitative measurements, and we would like to do quantitative measurements. In this work we have therefore looked at a different technique. This technique is similar to impedance scanning microscopy and electrical impedance scanning, as in that a probe is moved over a sample and that the impedance to some reference is measured at different positions. To further understand this technique, we have analyzed it using a model. For this technique, we first make sure there is a potential over the sample by applying voltage over it. Then we measure the voltage distribution by scanning over the sample, and then later we can use the gradient of the voltage distribution to calculate the electric field that was generated inside the 3D printed sheets. Then, in order to give a more quantitative result, we measure the current that goes through the ground and use that to normalize the measured potential. I know this sounds like we're calculating a resistance, and we are. However, a resistance is generally seen as a property of some material, which in this case it isn't. It is a property of the entire system. Therefore, we choose to use the normalized potential. Now, to know what we might expect, we have simulated an under-extruded sample where the traxels only touch near the corners. This simulation showed that we could expect a potential distribution which is largely constant in the I direction. This makes sense since the conduction in the I direction will be much better. Now, if we calculate the gradient of this to get the electric field, the x component of this field will very clearly show the location of the voids where The X component of the field will very clearly show the location of the voids between the thresholds. Of course, we still have to check this, so in order to do that, we printed a sheet using a die-based 3D printer. We printed it on top of a standard Delrin plate that we probed using the touch probe of the printer to make sure we were printing at the right height. The print was then sliced using a custom slicing script and intentionally under-extruded to get a lot of anisotropy. After printing, it was connected to the measurement equipment using silver epoxy and copper tape. Next, we used a different printer, a Creality CR20 Pro, to move a ball head pogo pin which contains a small spring-loaded metal ball over the 3D print, and we swapped the model board of the printer for a Duet Maestro and used a Python script to make the movement and the measurement simultaneous. The impedance measurement is done using a TP-LCR, which is the name that we gave to a custom PCB attached to a TP Handyscope HS5. This custom PCB contains a transimpedance amplifier to measure the current through the ground and an instrumentation amplifier to measure the voltage of the sample. And the TP-LCR also uses the arbitrary waveform generator inside the TP to generate a multisign, and then the current and the voltage at these 8 different frequencies are demodulated in real time using a Python script. For this, the Python script makes use of the QP library to do the calculations on a NVIDIA T1000 GPU. So now, what do the results that we get from this look like? First of all, there is quite a bit of data produced this way. Because of the multi-frequency measurement, the voltage distribution is simultaneously measured at 8 different frequencies, and of course this distribution has a real and an imaginary part, so that's 16 graphs, and the real part indeed does look very similar as the simulated results, as in the potential is the smallest in the bottom left corner and largest in the top right corner. And we also see that the imaginary part does also become significant after 100 kHz. Then now, if we use the gradient to calculate the electric field from this, we see very clearly that the real part of the electric field in the X direction fluctuates at an interval equal to the line distance. And interestingly, the same happens for the real part in the y direction at the higher frequencies. Then there also is the imaginary part of the electric field. It should be noted that this part is much smaller as the real part in all directions, so that measurements will be a little bit less reliable. However, it can still be seen that for some reason the complex part of the electric field in the X direction is much larger on the right side of the sample. Now, which conclusions can we draw from this and what can still be improved? Well, first of all, we have shown that this technique is well suitable to do quantitative measurements of the electric field distribution inside 3D printed conductors. Also, we can conclude that it produces a lot of data. One measurement gives the real and imaginary part at 8 different frequencies, so that's 16 plots. Also, we have seen that this data can be used to detect local defects in the print, such as improperly connected lines that we see here. However, we should realize that with the current method, we only get the electric field. In the end, what we need to really be able to say something about the quality of the part is the resistivity. This might be achieved by simultaneously measure the electric field due to a current from multiple directions and coupling that to an inverse FEM simulation. At the moment we can't print any more using the printer that we mounted the pogo pin on because it's in the way of the print head. However, if we would mount the pogo pin as a separate tool on the diabase, it might be possible to measure after every layer, and with some processing this might give us an idea of the 3D electric field inside the conductor.